All right, now I'm doing it. All right, sorry about that. Good call. All right. All right, so we have here entropy, or the change in entropy. All right, so it's a measure of disorder. Okay, so if we have this S being positive, or delta S, okay, if this S, whatever the units are, okay, it's energy, so joules per mole or kilojoules per mole. If this S is positive, we say that this is a spontaneous process. Okay, that's what you're looking for. Okay, something that's more getting towards disorder. Okay, more disorder. If this S or delta S is negative, that's a non-spontaneous process. Okay, you need to put in the work to clean that kitchen sink. You need to put in the work, the energy to make that bed in the morning. Okay, the atoms need to put in the work to arrange themselves to become a solid, very ordered. The atoms need to put in the work or somehow get something from inside their own internal system to create a crystal, which is a very ordered substance. Okay, so that would be a negative value for that energy, for the entropy. So a non-spontaneous process would be a result or a reaction that leads to more order. Okay, more order. So coming back to entropy, or delta S, change in entropy. Okay, we'll have three states of matter: solid, liquid, and gas. Okay. Okay, which do you think has the most entropy, most disordered? Which would have the highest entropy? Gas. Okay, this we would expect to be more positive. Okay, just as a state. We're not talking about change in entropy, just entropy by itself. This would be most entropic. Why would a gas be most entropic? Why? Okay, what do we know about gases? Okay, how are they? Okay, are they moving around? Are they diffusing around? Okay, there's a gas here, there's a gas there. They're hitting one another. They're hitting the walls of the container. Okay, they're colliding with one another. So there's a lot of motion. More motion, there's a tendency towards more disorder. Okay. If I breathe out CO2, I breathe it out. If I open my mouth, will that CO2 come back in to my mouth? That CO2, that oxygen, whatever I breathe out, it's gone. Okay? So it's out into the atmosphere, and that's a disordered transition. Okay, which do you think would be the most ordered? Okay, how are the atoms arranged in a solid, if you remember from that PowerPoint? So this would be maybe negative, or somewhere in between. The atoms in a solid are arranged very, very nicely, very compact. Okay, do you remember that lab on density of a solid? I did not go over it in lecture, but there is a lab where you measured the density of solids. And what did you calculate in those density of solids? You calculated unit cell dimensions. These solids are actually layered like bricks in a brick house. We call those individual bricks unit cells. Okay, inside the atoms are packed. Okay, they're not moving anywhere. Okay, maybe you can change the temperature and get a little wiggle or whatever here and there, but those are lattices. Okay, a crystal, diamonds, right? Diamonds is the most ordered substance. Okay, those unit cells are like lined up. so perfectly, so rigidly. So this is very ordered. Okay, so it would have a minimum entropy. How are the molecules arranged in a liquid? Okay, the molecules in a liquid, okay, are kind of in between a solid and a gas, so it would be intermediate in terms of its entropy. Okay. So if we're going from a solid to a liquid, okay, that phase transition, what would the change in that transition be? Would it be positive or negative, going from a solid to a liquid? Positive or negative? Positive, because going from a solid to a liquid would be a positive entropy. So instead of individual S here, we'll have the change. So this reaction will have a change in entropy that is positive. Okay, what about going from a liquid to a gas? Okay, it's going to be positive. Okay, the sign of that number will be positive. Liquid, the molecules are, diffuse, but in a gas, they are very diffuse. Here's something. What if you take a liquid and you add something to dissolve it in water and make it aqueous? Aqueous. You know what aqueous is, right? You take salt and dissolve it in water. Or you take any molecule and dissolve it in water. Would that be more entropy or less entropy, this transition, this change in entropy? More or less? Are we getting more order or more disorder? More stuff means more what? More stuff means more disorder. So this too would actually yield, this transition would actually yield a positive entropy. All these three phenomenon imply the system is heading towards more disorder. Here you just have some molecules of liquid floating around in the liquid. Okay. Now you have the molecules of liquid floating around in the liquid, and then what do? Okay, we add, some salt to make it dissolve, and we have aqueous. More stuff, more disorder. So it's kind of intuitive to think about it, or counterintuitive. It turns out there's more mass, there's more disorder. Something that's lighter in mass tends to have the atoms arranged with less space, less constriction. Something with more mass is kind of big and bulky. Okay, so that would lead to something that's more disordered. What do you think would happen if you raise the temperature of a reaction? More disorder or less disorder? More or less. Okay, if you raise the temperature, the molecule gets more motion, and more motion means more disorder. Okay, more motion, more rotation, more vibration across its bonds. More translational motion means it can go left to right or up and down. It can spin faster. All of these are tendencies towards more disorder. Okay, so you raise the temperature, that's also more disorder. Okay, so all these three phenomenon contribute to something where the tendency towards more entropy, okay, more entropy. All of these are increases in entropy. Okay. We would expect the delta S to be positive for this scenario. Okay. All right, we'll go over some example problems on entropy S. Okay, this is new for us here, entropy disorder. Right, finally, we have the final thermodynamic parameter, and that's delta G. Okay, this is called Gibbs free energy. Okay, gives free energy. So this is the final judge. Okay, this is the final judge. Okay, what do I mean by final judge? This will tell us whether the reaction will be favored energetically or not favored energetically. Okay, and that is what thermodynamics actually is. Okay, what is thermodynamics? What is this course that Irwin will have to take many years from now? Okay, if he's not jaded or cynical. Okay, he's really brave. Okay, but those that take the hard path, they get stronger. Okay, what is thermodynamics? Okay, it's really asking, will the reaction be favored energetically? And this delta G, I'd like to convince you, tells us this. Okay, will the reaction be favored energetically? Okay. Will the reaction be favored energetically? Or, if you want the reaction to move towards the products and if you want the reaction to move forward, will it require energy for the reaction to move forward? So that, in essence, is thermodynamics. Okay, so this delta G takes input from enthalpy and entropy to answer the ultimate question. What is the ultimate question? Will this reaction go to products? Yes or no? This tells us this delta G. And the equation is this: delta G is equal to delta H minus T delta S. Okay, so this final judge, Gibbs free energy, will take enthalpy information, okay, the enthalpy of a reaction, the entropy of a reaction. In some cases, you can make a reaction move to products if you change the temperature. You know, if you increase the temperature, you can make the reaction move to products. So this T here stands for temperature. Okay. So finally, let me just write that here. By the way, this also works for standard state. This not. Okay, this means standard state, which means you look it up in your textbook, all those values, okay, for standard state conditions. So whether it's non-standard state or standard state, this is the final equation that tells us will the reaction move to products or not. If this delta G is negative, a negative sign, and we're talking about joules per mole or kilojoules per mole. Okay, if this delta G is negative, yes. The answer is yes. This reaction will move towards products, and we call that an exergonic reaction. Okay. Means this reaction is going to go. If you plug in your delta H here or delta S here or your delta H at standard state, which you can get those values at the back of your textbook or the internet, or the delta S at standard state, you can get those values in your textbook or in the internet. You plug those numbers in, you plug in your temperature. If that final answer is negative, this reaction will go to products. Okay, you don't need any interference. Okay, you can do nothing and we'll go to products. Okay. If this delta G is positive, that means it does require energy. Okay, and that's called an endergonic reaction.
And that would be
It would be energetically unfavorable. That is correct. That's very correct. Okay, so this reaction does not move forward unless you supply it with some energy. I know in cell biology or biochem we say if it's an endergonic reaction, in a particular reaction, you need some other energy source. Usually an exergonic reaction will power an endergonic reaction. Okay? Like that's why when they hydrolyze ATP, it releases this energy. And that energy can make an endergonic reaction in the cell go, converting, I don't know, glyceraldehyde to dihydroxyacetone, whatever it may be. Okay? Which would be normally endergonic, but when you hydrolyze ATP, it releases energy that's exergonic, and it can power this reaction. So yes, you're correct. Reaction is energetically not favorable, and the reaction favors the reactants. So this is what we're going to be talking about here. Ultimately, our goal is to calculate delta G. But you notice it takes inputs from enthalpy and entropy. All right, really quickly, 2 minutes here. Okay, here the delta H is exothermic, which means it releases heat. But what would the delta S be? Okay, we got a gas, and it's going to one gas and two liquids. So would that be positive or negative? It would be negative because you're making a liquid. See what I mean? What about this? Okay, you have something that's aqueous, dissolved in water. This OH minus is dissolved in water, and it's making pure liquid, nothing dissolved in it. What would that be, positive or negative? Liquid is a pure substance. This is H plus dissolved in water. This is OH minus dissolved in water. What would this be, positive or negative for the change in entropy? Okay, it would be negative. You're making something more ordered. Here you're making something more ordered. Okay? What about going from a solid to a liquid? Would that be positive or negative? Okay, that will be positive. Okay, solid is ordered. A liquid is not ordered. Okay, the molecules are every which way. But notice that this is an endothermic reaction, so this requires heat. What about this one? You have a solid going to an aqueous. You have one solid going to not one, but two aqueous or an aqueous. Would the delta S be positive or negative? That is correct, positive. A solid is ordered, aqueous and aqueous are disordered. Okay, so, we'll take our entropies, we'll take our enthalpies. This enthalpy is positive, so it's endothermic. We take our enthalpies, we take our entropies. Okay, if there's temperature information, we'll look at the temperature and we try to gauge whether the reaction will move. So delta G takes entropic inputs and enthalpic inputs, entropic and enthalpic, to make the determination whether the reaction will go to products or not. All right, I am out of time.